Okay, so hopefully at this point you have come to some answer for our bell work today. What causes the tides? Are tides the same everywhere in the world? And why do you think this information? What experiences do you have that lead you to believe your answers are true? And we're going to hopefully clarify some of your answers throughout these notes, all right? So, tides and ocean currents. Really, I could teach for a whole week on tides, and ocean currents even longer, but we're gonna combine them all into one little presentation here. We'll do some more stuff with them in the next few days, but let's get into it. Okay, so the first part is to explain. We're going to be explaining how the tides are produced, how the alignment of the Earth and Moon and the Sun, and what's called coastal geomorphology. That's the shape of the land on the coast. Coastal geomorphology. Seems kind of long and wordy, but it's not. Wind, air, pressure, all those things affect the tidal range. Size of the water body, that's called fetch. If you have a greater size water body, you're going to get a different amount of wind, different amount of water flow, currents, all those things. So what are tides? Okay, it's pretty obvious. We're from Florida. We're from a country that's a country. Woo! We're from a state that is pretty much, it's a peninsula, right? So it is surrounded on three sides by water. So we have possibly more beach than any other state in the Union. I'm not sure about Alaska, but we have quite a lot of beach, waterfront. So the tides are everywhere. Tides are life. If you have ever gone boating or ever gone fishing or swimming, you at the beach, you know about high tide and low tide, at least minimally. And if you've gone boating, you probably know a lot about tides because it can mean the end of your boat and your life if you don't watch the tides very well. Okay, so it's obviously the vertical movement up and down on the coastline, and it's due to the gravitational pull of the moon and the sun. Would there be tides if there was no moon? Yes, but they wouldn't be as drastic. Would there be tides if there was no moon or sun? That would require a little bit more information. There would definitely be some currents, some movement, but it wouldn't be as, it might even be undetectable at most times. So you need that gravitational pull, and I'll show you what that means. And then of course the tidal range is the difference between the high tide and the low tide. And that varies from day to day, changes daily. So we're going to talk more about that as well. This is the Bay of Fundy in Canada. It has the world's largest tidal range. You can see it's just amazing. We don't get them like that here. At one point you can walk to the lighthouse, and the next point you can't. And same here. At one point, at low tide, you can walk safely around these stacks and arches. But at high tide, you would obviously need a boat or kayak of some sort. Okay, so what is the tidal range affected by? These people, these fishermen, in the Bay of Fundy, have to deal with this tidal change. They have to plan their entire day and fishing trips which is their livelihood, right? On the tides, because obviously they can't go in or out at low tide. And if they get trapped in, they can't go out. And if they get trapped out, like if they go out now, and they don't plan it right, or they don't watch the time, and they're out there in the ocean, out where the water's deep, they won't be able to get back for 6, 8, 12 hours later. They'll have to stay out there and then wait for the tide to be deep enough for them to be able to get in. And this is all because of the alignment of the Earth, Moon, and Sun. So you get this thing called a tidal bulge. The moon and the sun, especially when they're lined up in a straight line, are pulling, tugging. Anything that has mass has gravity. And the more mass it has, the more gravitational pull. Now, the moon is about 250,000 miles away from us, or 350,000 kilometers, roughly. The sun is 93 million miles away, but it is a lot bigger. 1 million Earths can roughly fit in the sun. So we're talking about, this is not the scale, right? Obviously the ocean's not that big either, but this is just a diagram showing you that when they're lined up, you get a pull on both sides, which makes your higher high tides and lower low tides. But when the moon is at a right angle, now you're getting pulls from 90 degrees, from, not opposite directions, but 90-degree directions, which makes that tidal bulge shrink a little bit. And so you don't get as high tides and as low tides. And so this would be a monthly cycle, or every other week or something like that, because this would be once a month. That would be once a month. Then the moon would go here. Then you'd be getting twice as much pull from the same direction, so you'd be getting higher highs and lower lows again. And then when the moon goes back around here, because it's a 1 month cycle for the moon, right? You'd get very similar to this tide. These are called neap tides. Neap tides are the weakest. Weak and neap, I guess, rhyme. So that's one way to remember. And spring are the highest ones. Spring brings the tide. How about that? Spring and bring, and weak and neap. Neap. So what does coastal geomorphology have to do with any of this? Okay. So as the coast narrows, the water gets piled up on itself. You can see here, all right? I know these are more interesting too, and I'll explain these in a minute, but as the coastline narrows, the water piles up, and when the tide comes in, it creates this wave effect, almost like, this is what a tidal wave is. Many people confuse a tidal wave with a tsunami, which completely different, we know at this point, because tsunamis are caused by, earthquakes, okay? And tidal waves are tidal waves. I have seen this in Canada, not in the Bay of Fundy, but just south of that in Nova Scotia. No, where was I? Newfoundland. No, wait, hold on. New Brunswick? Anyway, somewhere over there, just outside of the US in Canada, there is a narrowing of coastal geomorphology. And I was able to watch, and people lined up all the time. It's this, whole thing in these places. And oftentimes the waves are so big that people will surf them. This guy is this is not a tsunami, this is a tidal wave, okay? And his name is Richard. He is a Canadian newscaster, like a TV news guy. So he was doing this just to show what tidal bores look like. Now this angle is a perception thing. He's not really in danger. That is kind of much farther away, and so, but he obviously makes it out of there. But it's pretty scary. It looks really scary, right? He looks like he's Moses or something. But this is really amazing. They do this all the time. They surf it, and they've got canoes out here and stuff, and jet skis. So it's pretty wild. It's called a tidal bore, and you'd have to go to Canada to see it. I think that's the closest one. There might be some other ones, but I'm pretty sure it's Canada. So the wind, air pressure, and size of the body of water also affect the tide. So let's check this out, okay? So obviously increased wind speed is going to push water. You maybe experienced this in hurricanes, if you ever lived in a hurricane. The wind, the force of the wind will actually pull water out of an area or push it into an area, as well as air pressure. So when you have high air pressure or low air pressure, this is a hurricane, so this would be a low pressure system. When you have low pressure, you're going to increase the tidal range, because this is like exaggeration, but it's showing you the water piles up. This is what storm surge is. Air pressure causes storm surges. And you've got a wind-driven surge and a pressure-driven surge at the same time. And as water approaches, it piles up, causing that tidal surge, which can raise, depending upon the strength of the storm, can go 12 feet sometimes. Most people die in hurricanes, not from wind, but from flooding, believe it or not. Okay, and then of course the size of the body of water. The larger the body, so like oceans and seas and gulfs, they're going to have greater tidal ranges. Smaller bodies are going to have little to no tidal range, particularly lakes. You're not going to have, even at the Great Lakes or Lake Okeechobee, where you can stand on one side and you can't see the other no matter how hard you try with the naked eye. The day will go by and you're not going to see a level of water because it's just too small. It's not enough to affect it. So here's spring and neap tides again. So we just introduced them last time with the alignment of the celestial bodies, okay? But here is a more precise representation of what's going on with the tidal bulge. So, and what's good about this one is the yellow is showing you what the solar tide is, and the pink is showing you what the lunar tide is. The moon causes more tides because it's closer than the sun. Even though the sun is bigger, it's much farther away, 93 million miles on average. So yes, if the moon was not here, we would still have tides, but it wouldn't be as drastic. So the moon's monthly rotation is what's causing these larger fluctuations, these tidal range changes. So again, the spring tide brings the largest tide, spring bring, okay? And then the neap is the weak. The neap is the lowest, smallest tidal range. And both of them occur twice a month, as you can see here. Spring tide, greatest gravitational pull. Neap tide, weakest gravitational pull. Straight lines, right angles, and then the phases of the moon. Yes, you have to know which phases of the moon are responsible for causing these two different kinds of tides. And obviously if the moon is here, it's going to be a full moon, and here in a straight line it's going to be a new moon, okay? And then here is going to be a quarter, and first quarter, and then third quarter, okay? All right, that explains spring and neap tides in a nutshell. Now you're going to have to be able to interpret tide tables and graphs, okay? We're going to do a whole graphing lab activity on this. This is Boca Raton, September 10th, which was 10 days ago, and September 9th. This is in the Philippines, so I'll show you that in a second. So when you look up online, like right now you can look up on your phone, please don't, but you can. I just did this last weekend when we were determining what the tides were when we were going to the beach. You can see when the low tide is going to be and when the high tide is going to be, how long it's going to take to get between the two, and obviously what time of day that's going to happen. So here you can see that you have two high tides on September 9th, and they're about 12 hours apart. And then two low tides, but this one's the next day, about 12 hours apart. But it's not exact all the time. It changes throughout the year. So on Thursday it was 11:29 a.m. On Friday, it's 45 minutes later, the high tide. And these are pretty regular, but sometimes the high tide will be lower, and sometimes the low tide will be lower, and low tide will be higher. So it all depends on the positioning of the moon at the time, okay? And so here's the moon cycles, lunar phases, new moon, which you're gonna get a spring tide, full moon, spring tide, and then the first quarter and the second quarter are going to be your neap tides. And this shows you the tidal range from lowest to highest throughout a monthly time period, okay? And that's in meters. So what we're gonna do is we're gonna get the month of October for Boca Raton at the beach or the inlet. And we're going to graph it, and we're going to be able to interpret that graph once we make it. So just looking at it is one thing. Making it and then answering questions is a higher level, okay? It's gonna look like this. So actually this is for September. You're going to get a new one for October because October's coming up, okay? So in your notes, you have to answer these questions, okay? So we'll do the first one, and then you guys, after these notes are over, you're going to work on this together, okay? So calculate the tidal range on September 6th. So this is September, so you would go down to September 6th, and you would go across, and you would see the high tides are on this side, the low tides are here, the moon phases are over here, and what time the sun rises and sunsets is over there. But we really want to focus on the moon phase. That's really most important. So from 9:20 in the morning, you had a high tide as well as 9:48. The high tide, the highest was at 2.6 feet, okay? And that's not meters, because that was meters. That'd be like 9 feet, and we don't have tidal ranges that great here. And then low tide, the lowest was below the normal was minus 0.1. So you would have to pretty much just subtract, find the difference between that number, and that's your tidal range for the day, okay? For September 6th. And you can figure out the rest of them after the notes, okay? So let's continue. We're about halfway there. So describe, again, we're on the same, oh no, this is different now. Yeah, now we're talking about Coriolis effect. So, and the fact that it really comes down to this, okay? Because the Earth spins, did you hear me? Because the Earth rotates on its axis, large bodies of water and large bodies of gases, I guess we'll say, are affected by the Coriolis effect. Little things are not. You may have heard a misconception that toilets drain in the opposite direction in the southern hemisphere, like in Australia or South Africa or South America, okay? South America. That's not true. Toilets drain in a particular direction based on one fact only. How is the toilet made? What's the shape of the bottom of the toilet? Will determine which direction the water goes down. Not affected by Coriolis effect. The only thing affected is large bodies of water, like oceans, and large bodies of air, like the atmosphere, and parts of the atmosphere. And that's why you have a certain rotation in the northern hemisphere, clockwise, and a counterclockwise rotation in the southern hemisphere. And you can see it's the same in every ocean. So in the northern Pacific, it's the same thing for the most part. And then down here in the Indian Ocean, same thing, okay? And then you've got deep currents too. So you've got surface currents versus deep currents. Deep currents are driven by other things besides the Coriolis effect. Deep currents are driven by pressure differences, salinity differences, temperature differences, okay? So winds create the surface currents, and cold surface currents move from high latitudes to low latitudes. So you can see cold is the blue, and warm is, it's not hot and cold. This water's not hot, it's warmer, okay? And that water's not, it could be freezing, it's close to freezing. But the words cold and hot are, it depends upon your perspective. So that they're subjective, okay? They're not objective. So just be careful when you use those words when describing something. Warmer and colder would be probably best words to use here. So colder water is going to pretty much go down towards the equator because it's more dense, okay? and everywhere, in every direction. And same here, it's going to go in this direction. It's going to flow because the warmer is being created here, and it's going to move in this direction because of the Coriolis effect, because of the spinning of the Earth. Okay. And then again, warm, like I said, warm goes from low to high latitudes. And again, dense water, cold, high salinity, sinks and forms these deep currents over here. So there's two different types of currents. There are questions in this about this in your notes, so you're going to answer those as well later on. But this is just a really good map of the Gulf Stream, which is why we always have nice warm water along our coast here, even in the winter time, even though it's a little chillier than you'd probably like, than maybe you're used to at the beach. There's no way you can swim in the water in the ocean in New York, where I'm from, because it just gets too cold by the time you get this Labrador current coming down and chilling the water. The Gulf Stream kind of dips out and goes out here, but it comes around Florida, so we're always warm there. And you've got, these are all the names of the currents, okay? The Peruvian current, the Brazilian current, North Equatorial, the Kuroshio, the Eastern Australian current, the EOC, if you remember Nemo, Finding Nemo, the turtle. It's like the EOC, dude. Remember that guy? Okay, so that's the current that they had to ride to get down to Sydney. So answer those questions in your notes later. Upwelling. This is the movement, so it's a current, right, of cold, nutrient-rich water. That's really important to remember. Cold, because it comes from the bottom, and it's carrying with it nutrients that would not normally be there from the deep bottom sea to the surface. And it's caused because of this, okay? So you've got this perpendicular wind moving along the coast. You need also steep-sided topography, so there has to be some cliffs or mountains over here, all right? And what that does is it creates low pressure. It's kind of like how an airplane flies. I don't know if you know anything about aeronautics, but a wing is shaped so that air will flow faster over the top than it will under the bottom. And what that does is it creates a vacuum underneath, which gives the plane lift and keeps the plane in the air. Well, this kind of same thing is happening here. The wind is blowing parallel to the coastline. It's going to create a low pressure system, which is going to pull water upwelling, and then bring with it nutrients to the surface. That's what upwelling is. Here's the Coriolis effect again. I explained it kind of in words, but here are some diagrams that give it a much better, deeper meaning, okay? So it's all about deflection, or apparent perceived deflection at first. Deflected to the right in the northern hemisphere and the left in the southern hemisphere. And this creates gyres, or those circular currents in the water. The Coriolis effect creates gyres. Check it out. So imagine you threw a ball in a straight line from here to here. Florida is supposed to be there. They just dissed Florida and said, no, bye-bye, Florida. So you threw a ball in a straight line, but because the Earth is turning, the ball appears to take a curved path rather than a straight path over the land, okay? Same thing here. So I'm going to throw a ball over the North Pole. Okay? Hey, they included Florida there for once, all right? But because of the spin of the Earth, the ball over the surface of the Earth, the ball appears to be taking a curved path rather than a straight line. Even though in space, it's moving at a straight line. On the surface of the Earth, it looks like it's turning, okay? And that turn is pulling the surface currents and the air currents as well. Well, these air currents are kind of driven by convection, but when you go back to the ocean currents in a moment, you can see in the northern hemisphere, and it's all driven because of water, heat, temperature as well, but they spin in those directional movements because of the Coriolis effect. It's the effect that the spin of the Earth has on bodies of water, okay? Now you have to label this diagram in your notes, not your bell. You have to label the diagram in your notes, sinking cold water, salty water, okay? And that's going to create the North Atlantic deep water current. These are deep water currents. This is the global ocean conveyor belt. When we talk about, at the end of the school year, we're going to talk about human impacts to the environment. And this is going to be one of the things that we talk about. I did mention this in the past. If you want to see a dramatized portrayal of what could happen to the Earth if the ocean global conveyor belt is disrupted in some way, watch the movie The Day After Tomorrow with Jake Gyllenhaal and Dennis Quaid. I think it's a really good movie. But teenagers get caught up in this extreme weather change. It's one of those disaster movies, but I think they did a good job. But of course it's dramatized. So this is, okay, its importance of moving heat, seawater, is really about moving heat. If the Earth wasn't able to regulate its heat around the planet, some parts would get too hot and some parts would get too cold, and we would have massive hurricanes, and it might throw us into a melting stage where all the ice melts, or where even more strangely enough, it actually might create another ice age. Now in that movie I just mentioned, the ice age happens in like a week or a few days. It would take a little bit longer than that, probably in reality. But it could be some drastic changes in our climates, while not over a 1,000-year period, but in our lifetimes. So we have to be careful. So this sinking cold water sinks down and travels around the entire planet, heats up in different areas, and gets recycled back again. Sea to air heat transfer. So here you've got here's the Gulf Stream, which is a very important part of the global conveyor belt. Some of the heat gets transferred to the air and vice versa. So it's all a complicated integral process. It's almost like a balance, okay? Same with your body. If something happens in your body that messes up your metabolism, your balance, you get sick. Well, and you could die. Well, the same thing can happen with the Earth. It's not an infection, but it's a balance problem. So if the heat builds up or can't move on or whatever, major problems can happen, okay? All right, and that's what we're talking about here. So 9 tipping elements are now active. So these are things that can actually affect our global conveyor belt. So this is an animation of what I just showed you. So diminishing of the rainforest and the boreal forest in Canada, ice sheets and permafrost melting, Arctic sea ice melting. And this is a key point here, the Atlantic circulation. If this gets messed up, West Antarctic ice sheet, coral reef destruction. So all that stuff combined is we see happening right now. Not just because of man, but because of natural solar cycles as well. So there's a whole bunch of different play. Don't ever listen to one person when they tell you that this is going to happen. Climate change or global warming, and it's caused by this and that. It's a little bit of both. Okay? Don't be so one-sided. It's a little bit of nature as well as a little bit of man. Okay? All right. A few more, 3 slides left and we're done. So this is El Nino and La Niña. Yes, the boy child and the girl child. Boy child named so because it usually comes in December around Christmas, and so they named it El Nino. Okay? That's where the name comes from. And so these phenomena can affect the world climate as well, at least temporarily, when these events happen. So here's a normal year. Normally, where we don't have this process of El Nino, which I'm going to show you what it is in a minute. Normally we have winds that go from east to west. We have surface currents that go from east to west. Surface water piles up higher in Australia and Indonesia. So here's Australia. So this is the Pacific Ocean. This is where this happens. It happens in the Pacific Ocean, not the Atlantic Ocean. So make sure you're aware of where we're talking about here, okay? So this is a normal circulation. Trade winds blowing westward. Warm surface water piles up over here. Cold water pressing upwards against South America there, okay? You get cold, dry conditions in South America. Good upwelling off of South America because of the cold water and the crosswinds to the coast right here. And warm, wet conditions in Australia and Indonesia. I'm going to talk to you more about Florida in a minute, okay? So what happens when El Nino comes? The winds reverse. So again, here's a normal year. Here's an abnormal or an El Nino year. Surface currents reverse. Upwelling stops. So upwelling gives nutrients so the fish populations grow during upwelling times. But if upwelling stops, that's going to affect the fish population off the coast of South America and other places, and people are going to have less food, okay? And then the conditions change in South America and Australia and Indonesia. Down here, reductions in Atlantic hurricane activity. So now we're talking about Florida a little bit, a lot actually. So when you have an El Nino year, you have less hurricane activity in the Atlantic Ocean because you have increased vertical wind shear, which pretty much destabilizes hurricane formation. And it brings above average precipitation to Florida. So when we get an El Nino year, even though we're not getting as many hurricanes, we get more moisture in the air, which brings more rain, more moisture during the fall, winter, and spring, which is normally our dry season. It's not even hurricane season. We could go a couple of months without any rain at all in Florida in the winter. But during an El Nino event, it would make it wet, okay? And which would reduce risk of wildfires, which is good, but it would also increase the risk of flooding during that time of year. And then complete across the southern United States, you will get an increased storminess because if there's more moisture in the air, you're going to get more thunderstorms, which creates tornadoes, hail, which could reduce crops, and of course, lives and property, right? Severe weather in Florida as well. So that's what an El Nino does to our environment and to other environments in Australia and South America, okay? So warmer winters also in El Nino years. El Nino effects around the world. Less nutrients because of warmer waters, because you don't have the upwelling bringing the cooler, nutrient-rich water. So less phytoplankton. The phytoplankton are the little microscopic creatures that live in the water. The phyto, meaning plant, those are the ones that photosynthesize and provide half of the oxygen, possibly more than half, of the oxygen in our atmosphere that we breathe. Many people think that most of the oxygen comes from plants, like land plants, but actually it comes from phytoplankton in the ocean. So less food, and then fish will die. Warmer waters also cause zooxanthellae to die. Those are the symbiotic organisms that live in corals, that give corals their color, and also provide corals with food. They photosynthesize. So corals kind of have that symbiotic relationship that helps them actually get food from light, although they get most of their food from filter feeding. Or not filter feeding, but they have like stinging tentacles. So they just they go like this in the water and grab particles out of the water. But anyway, if their zooxanthellae die, then they die. They get bleached out, and coral bleaching, you may have heard of that. Cooler and drier weather in Indonesia, that causes droughts and fires if there's not enough moisture. And then flooding and landslides in South America because of the increased moisture, okay, and warmth there. So normal conditions and then reversed El Nino conditions, moving that moisture to different areas. This is what the sea temperatures look like, much warmer sea temperatures off the coast of South America. There's Florida up here, which affects really the whole world when this happens. And a thermocline also changes shape. We know about the thermocline, it's that change in temperature at a certain level in the water. That will also be affected during El Nino events. And then La Niña is kind of the opposite. This causes, not the opposite, but, well, yeah, I guess it is. It's a cooling. So rather than a warming of this region, you get a cooling, and it creates, the warm water moves to a different region, moves off, and you get the jet stream, which is the upper level winds that drive weather patterns. It moves northward and weakens. During the winter, the South Seas become warmer and drier conditions than usual. North and Canada tend to be wetter and colder. Waters of the Pacific are colder and contain more nutrients than usual. So it's all about balance. When the balance gets thrown off, patterns change, okay? And it is true, by burning fossil fuels, we're adding carbon dioxide to the atmosphere, which traps in the sun's heat, which can drive some of this to happen at a more drastic and more frequent rate than if we weren't burning so many fossil fuels, okay? And that is our show. Your job is to obviously go back and do those two little parts in the notes. And then we have something else planned for this.